Okay, so hello and welcome. Here we are, third round 3. Let me see if I can. Let me check the audio, make sure that's working. Then pop out the chat. Okay, let me check the audio, make sure that's working. Then pop out. Very good. Pop the chat out. So this is a pretty rough. This is kind of a rough one, man. So yeah, basically, here I am trying to solve this question, and I don't want to jinx it, but I suspect I may have solved it. So, first things first, let me want to show something before I begin. Just want to make sure it's, yeah, okay, that's fine. So that's good. Got the chat, I think everything's fine. I think I can show what I'm doing here. All right. So I've spent like many hours on this now. I think it's upwards of like 10 hours on this question. This one was a bit tough for me. This is a bit tough one. I spent a couple nights thinking about it now too, quite a while. All right, so I'll read it again one more time, and then I'll explain what I think is the solution, what I suspect is the solution. Moving stones until consecutive 2. There are some stones in different positions on the x-axis. You are given an integer array stones. The positions of the stones, call a stone an endpoint stone if it has the smallest or largest position. In one move, you pick up an endpoint stone and move it to an unoccupied position so that it is no longer an endpoint stone. In particular, if the stones are at, say, 1, 2, and 5, you cannot move the endpoint stone at position 5, since moving it to any position such as 0 or 3 will still keep that stone as an endpoint stone. Game ends when you cannot make any more moves, i.e. the stones are in 3 consecutive positions. Return an integer array, answer of length 2, where answer of 0 is the minimum number of moves you can play, and answer 1 is the maximum number of moves you can play. And the number of stones is 10,000, it's relatively large. They could be also between 1 and a billion, again, kind of a large range. The values of the stones are unique, and this has a relatively low acceptance rate, not too low, but a very low submission rate. A lot of people skipped this one. A lot of people gave up on this one. This one is a tough one, I think. Not ranked hard, but definitely one of the more challenging questions, in my opinion. Maybe not as difficult. Some of the hard ones are probably easier than this one, quite frankly, and vice versa. It's kind of hard to tell. The mediums and hards, they do have some level of overlap, but this one's definitely well into the overlap range. Okay, so that's the question. Now, for what I think is the solution, basically what I went with is I decided, okay, let's sort the stones. Let's create a difference array of the stones to give me an idea of an array of the gap sizes between the stones. So this is an array of gap sizes. These are the gaps. Now, the maximum result is not too hard to figure out, I believe. I kind of explained that earlier in the other video. Basically, you could design an algorithm that takes the most amount of time, and it's related to the smallest stone and the largest stone, as well as the penultimate stones, the second to smallest and the second to largest. And there's always at least 3 stones, so it doesn't get too complicated, that calculation, which is nice. Yeah, I'm not going to explain that here. I'll just say it's not too hard to figure out. Basically, you just come up with an algorithm that takes a very long time, as long as you can imagine, which basically boils down to moving the stones in such a way where they're always as far to the side as you could possibly go, either on the left side or the right side of the interval. And then that algorithm, you can basically get an idea of how long that algorithm should take, how many moves it should take, and come up with an expression that relates that. It's not too bad. It's not too bad. I'm not going to explain it here though, because I explained it before already. What's a little more complicated is this algorithm, this approach, which consists of taking the gap array, running through it once left to right, and then reversing the gap array and running it through it again right to left. And this is going to be a 2-pointer greedy algorithm, or a 2-pointer algorithm, 2-pointer greedy algorithm, I guess is the way to say it. So what we do is we have the left side or right side. So there's like a few important variables. There's a total sum, prefix sum. It's a total number of stones that are going to be shifted. And then there's C, which represents the current gap that we're considering. So what I'm going to do is I'm going to look at each gap I'm going to look to the left and have some sum to the left, and then also some number of elements not in that sum and also not including that gap. And these elements are all the gaps themselves, right? And and count the number of those other gaps, because each gap, if you move the stone, the gap disappears. So we have a total number of total number t of other gaps to consider, total number s to consider the sum of the gaps of a certain subsection, subarray, and then c is the current gap that's under consideration. And so the idea is to calculate a difference between t and s, because I can move all those other stones, all those other gaps, stones that constitute those gaps, into the size the s, which is the sum of all the gaps. So I could move all those in there, and the difference is how many stones are left over. And then I can also take a look at the gap I'm currently considering, and I could say, okay, I'm going to loop on. I have a left side and right side of the gap elements. If my difference is less than 0, meaning I have more gaps to fill than I have stones to fill them with, then I need to move my left side down and start putting those stones in the left part of the sum. Start reducing the total number of gaps I'm considering, and increasing the total number of stones that I'm going to move. Right. So I do that repeatedly until the difference is greater than or equal to 0. And actually, I don't know if I guess I do need this here. And the way to do that is just subtract the left side from the total sum and add that stone into t, the total number of stones I'm dealing with, and then recalculate the diff each time. So do that repeatedly until I'm back to a position where I don't have too many gaps to fill, right? So I get to a point where I can fill all the gaps. This is the part that's really interesting. We'll come back to that in a moment. Basically, how do we update the minimum result? Come back to that. And then after I've checked that particular sort of subsection, left to right subsection, where part of that subsection is going to be just C, which is it would be the rightmost element in this case, and the other part of the subsection is going to be the sum for S, and then everything else in the array is going to be added together to T to count the stones, the gap elements. Once C has been considered, I'm going to move to the right. This is this plus R, move to the right. I'm going to add that gap to S, and then decrement that stone from T. It's really, that stone wasn't in T to begin with, but I'm going to be considering, I'm moving C over, so that stone would then be removed from T, and the gap C is going to be added to S, and then update the difference again, and just keep doing that over and over again. I'll explain what this does in a moment. And so we do that from left to right, reverse the gap array, go left to right again, which is basically the same thing as going left to right and then right to left. Algorithm is a little bit complicated to try to do it right to left, so I thought it was easier to just reverse the array and do it twice. Simple enough. Okay, now this part is a bit sophisticated, kind of involved, and this is what I had wrong before, and it really took me like days to figure this part out. It took me a lot of time to really think this through. So if C, the current gap, is greater than or equal to the difference, and the difference is greater than or equal to 0, it should be greater than or equal to 0 after this for loop, but maybe it's not. So just in case, I have this here, because technically your L could end up at R, and then the diff is not 0, something like that. So, it may be possible for that to happen. I have to think about whether it is, but just in case it isn't, we just make sure that that's there too. So we're only considering the cases where we have enough stones to fill the gaps that are under consideration. If C is greater than or equal to that difference, that means that what's left can be placed in C, and that's necessary for us to actually complete the. That's necessary for me to actually complete the. What's that called? It's necessary to complete the sequence, right? To get to a completed game, right? Because if C is too small, then that means I have too many stones to move, and I won't be able to fit them all. I won't be able to fit them all without sort of basically moving C around or something like that, more or less, yeah, kind of coming to a different kind of consideration. Yeah, so yeah, in that case, basically a different part of the algorithm should consider that. Like basically in that scenario where C isn't large enough to fit all of these values in that are left over, that pretty much means that I need to either increment the, well, that would actually be this case if the diff is not negative. So the diff is not negative, but I just don't have enough room in C itself. That means I need to decrement the diff, make it smaller, by incrementing S by just going to the right by 1. Yeah, going to the right will increment S and decrement T until that case holds, which basically means that C is going to get, what do you call that? C is going to get popped. Basically, yeah, that if that scenario occurs where C is less than the difference, that pretty much means that C is going to be added to the gaps, or the C is going to be added to S for the more gaps, to create more gaps, and one less stone is going to be popped, one less stone is going to be pushed. So yeah, it pretty much means we need more gaps in that scenario. That's basically it. You're not able to actually fit all of the stones in the gaps that are available, and so you'd have to just increase the gaps. So yeah, that's why C is greater than or equal to diff is the only consideration there, and diff greater than or equal to 0, again, as mentioned, like it's kind of if diff is less than 0, that means there's too many gaps to fill, and I would need to go in the other direction. I would need to reduce the number of gaps. Okay, so this is sort of the sweet spot, and in here what happens is you've got a few possibilities. C could be greater than or equal to the difference. If C is equal to the difference, that means that you can basically just put all of the diff values into C, and C becomes 0, that gap becomes filled, and we're done. And that just took T number of movements, right? We just basically moved all those stones and filled all the gaps, and we're done. That's if it's equal to the diff. If it's greater than the difference, then it gets a little more complicated, because what you can do, as long as this condition's not true, and this is a little bit complicated what's going on here, what can happen is I can do a kind of a special maneuver where it only takes one extra maneuver, one extra move to handle C, the rest of C. So if I just move all the other stones into the gaps that I have, which really would just be into C, move them all into C, there's still a gap in C that hasn't been filled, and I can't just move C over itself. However, if there's at least one other stone to move in the diff, and S is 0, or no, not S is 0, excuse me, if there's at least one other stone and S is not 0, meaning like there's another stone that exists that I can maneuver, there has to be another stone that I'm going to move in the difference, and there has to be a stone, a spot in S that I can move into the gap. So what I would do is I'm actually going to how does it work? It's like I can move. Oh, this might not be correct, actually. Like I said, this is really complicated. It's really sophisticated, this part. Basically, the idea would be what you'd want to do is you'd want to take the stone you're about to move into one of those other gaps. Instead of it moving into one of the other gaps, you're going to move it where you would want to move C, right? So C is actually a gap between two stones, but there's like a stone on the right. Let's just say it's on the right side, or it could be on the left side. It doesn't really matter. But if it's on the right side, let's say it's on the right side, and you have some other stone you're going to move. Instead of moving that other stone into S, wherever it's got to go, you move it right next to a right stone on C. Right, or not right, not there. I'm sorry. You put it where you want C to go, and then you put the stone for C into that other gap. So you kind of like crisscross these two stones. So that means you're going to put one thing into S, and that one thing that's going into S is going to be the diff value. And instead of putting that diff value into where S would be, and then trying to figure out what to do with C, you're going to actually put C into S, and then put the diff value where C should be, and then put S into. Put the diff value into where C should be, and then put C into where S is going to be. So these both have to be greater than or equal to 1. If these are both greater than or equal to 1, then you can do that maneuver, and forget about this for the time being, for the moment. There are other scenarios too that are similar. As long as you have something in diff, it's not 1, and as long as you have something in S. So diff necessarily, if S is 0, I think diff has to be 0, because if S is 0, that means T minus S is diff is T. That means the diff is T. And it's all the other stones that you're considering. And in that case, I'm just thinking about like when this is this or this. I think it's got to be, these have to be both greater than or equal to 1 for this to make sense. Just thinking, if C is greater than diff, that means that everything can fit in C. So you cannot perform this maneuver when, the way that I described it, when S is 0, or when, I think you can't do it when diff is 0 as well. If S is 0, you won't be able to do it. And it gets confusing too, because basically if you're able to perform this maneuver, then you only need one extra value, one extra move to handle C. If you can't perform this maneuver, it's going to be, you can't perform it when S is 0, I think, or diff is 0. Just thinking, if S is 0. Yeah, again, it's really complicated, this kind of part of the algorithm. When S is 0, you won't be able to perform that maneuver. You have to do an extra. I think this is an or here. I think this is an or, not an and. Yeah, if S is 0, you have to perform an extra maneuver because it depends on the value of C as well, or the difference between C and C and the difference. So, like if S is 0, and that means you can't put anything from the diff into S, and yeah, I mean, even if the difference is 1, if the difference is 1, no. Oh, that's so confusing. What's left over? What's going into C? Even if there's one element that's going into C, right? If diff is greater than 0, and even if S is 0 and diff is greater than 0, you can still do the swap that I was describing, because you could take that diff stone, put it where you want the If C is greater than or equal to 2, you can put the diff stone where C should be, and then one position over, and then you can put the C stone in the right spot. Yeah, so you can still do 2 if diff is 1 or more, and C is at least 2. You could still do this in one iteration. And even if S is 0, if C is 1 and diff is 1, right? Well, in that case, C is not greater than diff. And actually, you could do them both in one shot. It's just T. But if C is 2 and diff is 1, then it's the same thing. Then C always has at least 2. So if diff is greater than 1, diff obviously is always positive. So if diff is greater than 1, then you can do this, even regardless of what S is. If S is 0, yeah, so diff has to be 0 in order to not be able to do this. And if S is 0, then if S is not 0, then the other maneuver that I was describing can be done, right? So it's got to be both S is 0 and the diff has to be 0. So regardless of S, if the diff is not 0, then this works. This trick works. You can do it in one shot. You can do T plus 1. If S is 0, or if S is not 0, you don't care about what diff is, right? So suppose diff is 0 and S is not 0. If S is not 0, well, if S is not 0, that means, and the diff is 0, that means S and T are equal. And then, but yeah, because S is not 0, then you could do the other trick that I was describing, right? So if S is not 0, you could do the other, and diff is not 0, or diff could be 0. It's just S is equal to T if diff is 0, which means that T is not 0, which means that S and T are not 0. So you can do the trick. Okay. It's really confusing. But basically, yeah, if this condition is true and either of these conditions are not true, that implies that you could do the trick that I was describing, a crisscross trick, in order to take care of C in one extra move, which is C plus 1. Now, to handle that, suppose both of those are not true, or suppose both of these are 0, then you have another consideration where if both of these are 0, you need to perform one more operation, because that means that S is 0, and the difference between S and T is 0, which means T is 0, which means you have only one stone with some value C, and it's at least 1. Now, if that stone is exactly 1, again, you can just move one stone there and handle C in one iteration. You would just move from the left endpoint into the gap, and then you're done. So that's why C has to be greater than 1. If C is 2 or more, then the maneuver you've got to perform is take the left stone, put it in the gap closest to C, so the C stone, and on the right side, assuming it's on the right side, and then the C stone, you put it in the gap, but the last gap, and you can, it takes 2. So anything greater than 2 or more is going to take 2 extra moves to handle C, and that only happens when S is 0 and diff is 0. All other situations, you can handle that basically with one extra maneuver. It's a little bit sophisticated, but one crisscross maneuver, you'll be able to take care of C. I realize it's very confusing. It's like really involved. Yeah, the logic there is like, holy smokes. to try to do that in like a short period of time is like kind of crazy. Like I don't think it's that reasonable to be able to figure all that out in like a very short period of time. So yeah, that's pretty much what's going on here, is that you have some cases you can do it with just all of those stones get pushed in the right places. Some cases it takes one extra maneuver to handle the C value, and then some cases it takes 2 extra maneuvers to handle the C value. That's basically what's going on. And you got to really, really think it through to get through all the cases. And yeah, so let me run this to, it's quite a thing. Let me just run this. So this works for a bunch of randomized cases. Oh yeah, so another thing I want to show is that I have this script, bash shell script, to generate 7, it should be 8 cases, so eight different randomized cases. I used awk and srand and used the date to seed srand inside. I'm surprised that this worked for the awk script, because I thought that putting these extra characters inside would cause issues, but for some reason the awk script works out okay here. So yeah, it's just it's basically uses an awk script to generate as like a subroutine to generate these test cases, and using srand, and that's seeded by the CPU time in nanoseconds, and then for loop just does it 8 times, so I get this output 8 times, and I can just go ahead and go this here, make this source value appear, and then copy paste, and now I get a whole bunch of test cases, which is nice, because I kind of liked in the past that you were allowed to basically put like an infinite number of test cases in there, and then they limited it to about 8, which is about right. You probably should be just about 8, but that's like, so now I can get a pretty good amount of testing in here, and I kind of want to do a bunch of smaller cases where it's only just a small number of things moving around. Let's see. And then I want to go really small. So I'm just doing like fuzzing, because I think this is correct, but I don't actually know with certainty, because it's, like I said, that logic is like really involved. It's pretty easy to make a mistake there. You can't really be too certain with that, quite frankly. So let me make things a little more interesting. Get really down there. Really get down there in terms of like the distance. And I'm also fairly confident that the initial sorting, I don't have to worry about. Like, it's okay for these things to be sorted initially when I'm inputting these values. Also, I think the stones are, yeah, they're at least 1. I think I want to test some unusual cases. So I was saying before, the C value matters a lot, right? So I kind of tested this before, but let me do it again. So the C value, like if I had 1, 2, 3, 4, 5, right? That's just S is 0 the whole way through, and diff is, I don't know what diff is exactly the whole way through, but basically that's like a special case. Then let's put a 2 in here. So to have a gap of 2, you want to add 3, 5, 6, 7. To add, let's put a gap of 2 on the other side, right? Would be 6, 7, right? We could put 2 gaps of size 2, which puts me at 3, 4, 5, and then another gap of 2 would add 3. Oh no, this is 4. It's going to be 4, 5, 6, 7, or 6, 9. 2 gaps of 2. Let's do a gap of 1 on both sides. Let's do a gap of 1 on the other side. Let's do a gap of 1 on the right side. Yeah. 6, 7, I think, gap of 1 on the right side. No gap of 1 on the left side. Let's do a gap of like 10. Oh, oops, this should be 3. Oh, no. 3, 4, 5, 6. Yeah, I kind of did that wrong. I don't know, let's do a gap of like a much larger gap on the right side. Like, there's a lot of different things you could test here, for sure. Again, fuzzing is not bad. So yeah, I think I got it. I'm going to go for like just a very large test case quickly. Just do one of these. One with like 10,000, and we're going to make it pretty big. Let's see, 1, 2, 3, I think 1 million. This is kind of a big one. So now it's like 1,000. I think this is like thousands, millions. This is billions. This is too much. Too much. Too big. Should be at most like 2 billion. I think it's like half a billion. Yeah, that's fine. Half a billion's good. So now I gotta scroll up a bunch. It's gonna take a while. I don't know if there's like a faster way to get this into the clipboard, like to copy paste something into a clipboard. Oh, there we go. That's quick. Yeah, I don't have to scroll. Keep scrolling. Scroll. a lot of scrolling, man. Gee. Just keeps going. There you go. Ah, no. No. Okay, I did it wrong. Got a lot of scrolling to do. That's a lot of scrolling to do, man. Go faster. Like you can see the bar and the movie in the bottom right corner. I'm not sure how to. I'm not sure. I'm sure there's probably a way to do it to like have output go into the clipboard, but I don't know how to do that offhand. So there we go. All right. Let's try this. One test case that's quite large. I gotta say, computers are pretty impressive with some of the things that they do. It's really, it's like that's a lot of, it's a lot of just number crunching, man. Does this in 7 milliseconds. It verifies, processes all 10,000 of those numbers in 7 milliseconds. Wow, that's impressive. Yeah, I don't know what else to test here. I tested a bunch of random stuff. Tested. All right, I'm just gonna go for it. I don't know. It could be wrong. It's a good chance there's something wrong. Oh, got it. Nice. Nice. Yeah, some days I like really don't want to spend the time to try to figure out if something is correct or not. And then some days I just spend like multiple days trying to figure out that it's totally correct and fuzz it like crazy and all that. Got there. Beautiful. 15 milliseconds. Not too bad. All right, I'm going to submit this a bunch of times. Take a deep breath. I don't actually need to use all that memory, by the way. Obviously, I'm just moving through the gaps left to right. So this could easily be, you could compute these values on the spot. Don't actually need to store this in memory. You just would reverse the original array, I think. Yeah, it is kind of useful for this, but again, this could be calculated directly. Well, all of these values for D could be calculated directly, so you don't actually need the extra memory, which is cool. So yeah, I can always come back and maybe that'll speed it up a little bit, actually, if I remove the extra memory it's using. That's a big time sink with algorithms, is just accessing memory. Let's do it like 5 times. I'm going to try that, actually. I'm going to see if it's faster if I don't use memory. Yeah, I'll submit it like 8 times. It took me a long time. So I'm going to do this without the memory, the gaps. So D0 is going to be VS1 minus VS0. And the back is going to be Vs of n minus 1 minus Vs of n minus 2. Right? I think I mentioned that before. Oh no, yeah, that should be fine. So it goes right to left. So this number is larger, this number is smaller. And then I can say instead of D, it's just going to be of R, it's going to be Vs of R plus 1 minus Vs of R. And same thing here, it's going to be Vs of L plus 1 minus Vs of L. And I don't think I need anything else if I do it this way. And I can just reverse Vs. So this doesn't use any extra memory if I do it this way. Probably should test it over a bunch of test cases too. Wrong answer. No. Oh, come on. Oh, well, that's awkward. Whoops. Oh, it was a -1. Excuse me. Forgot about that. Each of these D values has a -1 in there. Totally forgot about that. Yeah, gap sizes. Gap sizes, there we go, okay. Can I reset the test cases? Maybe just go for it. I don't know. Tempted. Let me just do a few other ones. Now that I have this this script to do my testing, which wasn't too hard to put together, quite frankly. But now that I have this script, I prefer to do lots of testing before lots of extra testing before I submit things, just because it doesn't take that much extra time. In the past, I kind of thought about it, and I was like, oh, it takes so much extra time to do the testing, but it's not really that much extra time, quite frankly. With a script, it's pretty quick. All right, I'm gonna go for it. See if it works. Hey, that works too. Is it faster? Seems to be about the same speed. Let me try again. Uses a little less memory now though, which is what I wanted, because I think in theory, if you use less memory, it tends to be a little bit faster. See, this is linear time, no extra memory. Oh no, it's not linear. It's n log n. The sorting is the bottleneck as far as like speed, asymptotic speed. But these actually, oh yeah, I was gonna say you could sort it with counting sort, but actually you can't. You can't, because it's from like 1 to a billion, the numbers. So it's very large, these numbers, potentially. On the larger side, yeah, it doesn't really improve it that much, using the memory and not using the memory. Don't have to do that extra reverse. Let's try one more time. Do it one more time with the gaps pre-computed. I don't know which one's faster. Quite frankly, they seem to be about the same speed. Just got to do extra. Yeah, it's about the same speed. All right, I'm gonna submit it one more time. 1, 2, 3, 4, 5. So I suspect this has like a much cleaner solution out there. We could look at the solutions. I'm kind of afraid to, but yeah, this is pretty. It's quite an algorithm, quite a question. Yeah, I definitely want to. Definitely want to take a break after this. Definitely time to take a break. Yeah, pretty good. But what do I do? Let me see the solutions. Yeah. So yeah, my solution was not the fastest. It was like reasonably fast, but not as fast as it could be. 8 lines, sliding window with binary search. Whoa. Easy, fast. Let's do most votes. Sliding window with picture. And log in with detailed explanation. Sliding window. By no means be a medium question. Is it really medium? That's very funny. 7 lines. Mine wasn't 7 lines. Mine was pretty involved. Like 30 lines, but yeah, you could remove quite a few of these lines if you just don't initialize the memory. The max result is like a constant. I mean, you could also put these on one line too. It's another thing. Like a lot of these could be on the same line. Like all of these could be on the same line, just about. This could be like one line of code. Yeah, these also could be. All of this could be put over here or something. You could make this a lot more terse if you wanted to. It's not, but it's kind of is what it is. I think also if I inlined this function, that might be another idea, because having to call these two functions is probably slows it down a little bit. Yeah, and then not having the memory, I don't have to reverse. Oh no, I actually do have to reverse anyway. Yeah, it doesn't. Never mind. Yeah, I don't know. Let's see. Case of end stones. So he figured this out 4 years ago. Wow, it's a long time ago. Need to find a consecutive n positions and move the stones in. Idea led to the solution with sliding windows. Slide a window of size n and find how many stones are already in this window. Want to move other stones into this window. For each missing stone, we need at least one move. Generally, the number of missing stones, the moves we need are the same. Only one corner case is in this problem. Need to move the endpoint to no endpoint. One move it from 10 to 3. For case, we need to move 1 to 6 and 10 to 5. Okay. Yeah, that was the kind of crisscross I was describing before. Try to move all stones to leftmost or rightmost. For example, to rightmost, we move the A0 to A1 plus 1. Then each time, pick the stone of the left endpoint, move it to the next empty position. Position of leftmost stones, increment 1 by 1 each time. To leftmost is AN minus N plus 1. Time of quick sorting, time of sliding window, space. Whoa, this is really clean. Wow. Yeah, so the high he did very similar to what I did. Did a very similar thing. A little more involved, this calculation, but yeah, it's basically the same thing I did. And then sorting low and high. I don't know if this is this isn't a binary search. Let's actually look at the C++. That's probably better. This is a pretty interesting way of doing it, though. This is a lot cleaner than what I did. The solution's always so much cleaner. I spend so much time thinking about these things. Okay, so what? What did he do? All right, this is very, very clean, simple explanation too, which I appreciate. Slide a window of size n, find how many stones are already in this window. I want to move other stones into this window. For each missing stone, we need at least one move. Generally, the number of missing stones, the moves we need are the same. Only one corner case, we need to move the endpoint to no endpoint. So in this case, we can move 10 to 3. In this case, we have to move 1 to 5 and then 1 to 6 and then 10 to 5. Yeah, crisscross here. So what is he suggesting? So if you have j from 0 to n, while a of j's minus a of I is greater than or equal to n, increment I. I gotta sneeze. Excuse me. What's going on here? So here's a of j minus a of I. If it's greater than or equal to n, increment I. What is n? N is just size, okay. Is this, do you need this? What is this? I don't know if you even need that. Does that matter? So while the number of, this seems kind of confusing, this part, because okay, I think I understand. Like you're gonna fit all the stones into that range, right? That's the idea. You're gonna try to fit all the stones in that range. So you could just check the size of that range directly in this way. I think I get it. And the size of that range is, it's going to be a of j minus a of I plus 1 is the number of stones. And if that's greater than or equal, to n, then you could, if it's equal to n, you could fit n stones there. So if you subtract 1 from both sides, so if it's greater than or equal to n plus 1, then you can't fit the stones. You can't possibly fit all the stones in there. It's greater than or equal to n plus 1, which is equivalent to the difference being greater than or equal to n. Okay, I understand. So yeah, if that difference is greater than or equal to n, then it's not possible to fit all the stones there. Got it. In that case, you got to make the range larger. So the range is too small, is basically what this comes down to. The range is too small. You need to increase the range by incrementing I. Okay, that's fine. And then you just check at every value j, j minus I plus 1 is equal to n minus 1, and the difference, a of j, a minus I, is equal to n minus 2. I've got some things going on here. If now this is the difference in stones between j and I. So if the total number of stones in that range now, if that's equal to n minus 1, so you'll need one more stone, and the difference between a of j and a minus 1 is n minus 2, then you're going to update low to minimum of low and 2. So low ends up at 2. So low starts at n, and we're gonna yeah. So at most n moves, I think. Optimally. So that's another question. I didn't think that was necessarily the case, that that you'd have to do at most n moves, move the stones n times. It's probably true that that's like a good upper bound, because you could basically just move all the other stones around one stone, and that would take n moves, something like that. I kind of was trying to think of a good upper bound for the low end, but I didn't really come up with a good one. I wasn't really sure. So okay, that's pretty good. That's good. Yeah, it kind of makes sense. I probably should have realized you could do it that way. I didn't really think about it, but that's fine. Okay, so then you can say low is going to be min of low and 2 if you're looking at if you're looking in this range where, I think it's just this edge case is what he's talking about here. You're not adding to low, you're actually you're actually reducing the minimum each time. This case, and I think it's this case he's describing. So if the number of stones, that you're looking at between I and j inclusive is n minus 1, it's missing one stone, and so you're just missing one stone, and the size of your range from a of j minus a of I is equal to n minus 2. It's going to be, I think, n minus 2 means you're missing, it doesn't mean you're missing 2 stones. So what's confusing about this is that it's the number of stones that could fit in this range is a of j minus a of I plus 1. If you subtracted 1 from both sides, so that equal to x, subtract 1 gives you x minus 1 is equal to this value. X minus 1 equals n minus 2 means you have n minus 1. So if the range you're looking at is of how many stones you can fit there is n minus 1, yeah, maybe it would have been better if you just added a plus 1 here and then a plus 1 there. So that way it was like a sub j minus a of I is equal to n minus 1. Okay, I think I understand. So if you're missing one stone, and the range you're looking at is also missing one stone, right? So there's one stone somewhere else out there. Then you should be able to move that one stone in 2 moves, which is what's being described here. Yeah. And I is on the right side or left side? I think I is on the left side. Yeah, so this will be handled correctly, I think. Like if that stone, yeah, okay. So basically, if you have everything lined up and one stone kind of off the edge somewhere, that's this case. Then you got to just use 2 moves to line everything back up again. And this isn't like an inductive thing. Like it's not building off of previous states or anything like that. Like it's just literally just go straight through, and if that's the case, you can set everything up in that way. This is just like very directly handling that edge case or those edge cases, because it's setting low to the minimum of low in 2. So it's just ignoring all the other previous calculations for low and going straight to 2. Which is pretty interesting. So there's this if statement, and then otherwise, you just update low to min of low n minus j minus I plus 1. So that's pretty interesting. What is this here? This is like, you could get low down to 1. I guess it doesn't throw out all of the possibilities, but it's pretty. I don't know if low can get down to 1 if you end up here, quite frankly. But anyway, this is in all other cases. You have n, which is the number of stones, minus the range of the stones that you're operating on between j and I. So basically you would move all the other stones into that range, I think. That's what this is referring to. So the larger you can make this range. So I don't really understand this part. This is like the most important part. I kind of understand this part. This part is less obvious. So you're just moving all of the other stones into this range, and the number of stones that you're operating in that range are not going to move. That's going to be j minus I plus 1, and all the other stones are going to be moved in. I see. And the problem with that, though, is like that doesn't make them all consecutive. I think what it means is that you're going through every possibility, and at least one of those possibilities is going to end the game. Which is not obvious to me at all, that you could always do that. Like that's really not clear, that you would always be able to guarantee that moving all of those stones would end the game. Oh, I see. Okay, I understand now. So that makes sense. So it does mean that if you could move everything into this spot, it does mean you end the game, because the range size that you're operating on can only fit at most n elements. That makes a lot of sense. Okay, I think I understand now. And by the way, you could, in theory, move elements like to the side of the range. Like if the range is small, then all the other elements could be put outside of the range. And yeah, that makes sense. That's pretty interesting, actually. I didn't think of it that way. Oh. It's not obvious at all that you could do this, though. This is like really making some pretty strong assumptions here that are like really not clear. Wow. It's pretty clever. That's pretty clever. Yeah, basically the as long as the range is less than n, all the other stones can be moved like around that range to fill it out. This is basically what's being stated. And you can always do that. Interesting. Huh. The only edge case you have is this one where you've got your range all the way through and you just need to have an extra maneuver. This is pretty wild, man. I don't know what to say. Like I figured it out from my perspective, from my end, but like this was way more sophisticated. Not sophisticated, but just way more I don't know, like way simpler. Wow. Jeez. Too hard to solve in a 45-minute interview, seeing this problem the first time. This would be extremely hard if you saw it the first time. I think so. Why do we need this? Yeah, it's brilliant. I got a rough idea. The only corner case. When look, oh yeah, I kind of don't fully understand the corner case. Could use some explanation on that. That's fair. Not a very typical application of sliding window. Solution really shines. Yeah, that's really good. When looking for the lower bound, we simply want to find the sliding window which has the least empty space. We have to take 2 steps when there's only 1 stone outside the window and the stones in the windows are consecutive. Okay. Yeah, basically. Have to make, yeah, that's what he was explaining here. Basically all other cases you can always move those other stones in, and so you're just looking for the optimal range. That's pretty amazing, actually. It's pretty good. Let me try that one. I like that one a lot. This again, we can go back to just, don't need D for this. Do want to sort, min result could be n instead of a billion. Excuse me. Min r, max r. Let's make it a little more terse. And this is just a gap. V1 minus V0 minus 0 minus 1. And this is V of n minus 1 minus V of n minus 2 minus 1. And then what he went with was I and j. And while loop. So actually he put j on the right and I on the left, right? And this is just while the difference of vs of j minus vs of I. I'm going to make it a little more, if that is greater than or equal to n, or greater than n, really. Yeah, if you subtract 1, then it's going to be greater than n minus 1, which is greater than or equal to n. So let's do it this way. It's a little bit easier to understand what's going on. And then we just say if j minus I plus 1 is equal to n minus 1, so we're missing a stone, and vs of j minus vs of I plus 1 is also n minus 1, right? Both of these things are n minus 1. Then that means we've got to update our min. Oh yeah, he used low and high of itself and 2. All of the cases we're going to update to we're going to say move all of the values in that spot, j minus I plus 1. And that's it. That's the whole solution. Very straightforward. Pretty amazing. Pretty amazing. I used V instead of VS. I could have used V. This would be an extremely clean solution, and if you figured it out quickly, that would be like, I think this is why it's considered medium. Compiler error? Oh. I think, yeah. I think this is why it's considered a medium, is because you could actually do this really quickly. Could do it very quickly. Let's just do a few cases. And then the other cases, let's do 6 of these, right? 1, 2. Okay. Yeah, I mean, I don't know what to say. I'm gonna go for it. I'm pretty sure it's the same thing code that he had already. Yeah. Oh, it's not that fast. What's going on? Actually, on the slower side. What is going on here? 1, 2, 3, 4. That's very quick, very clean solution to program, but not much faster than what I had. Actually, what I had is relatively fast. 1, 2, 3, 4, 5, 6. There we go. That's fast. Okay, I was gonna say, I'm pretty sure this solution is a little bit faster than what I had. By the way, you could probably just do this too. Like, you don't need to make this an else. Oh, you know what? You do need to. Does need to be an else, because you could have a situation where this basically would be 1, right? N minus n minus 1 is 1. Yeah, you do need to have an else. I think if there's a way I could add this. Wondering. Does this work? I don't know. I think so. I'm gonna go for it. Maybe. Is it faster? Oh, yeah, it's still correct. It's a little bit better. Yeah, it's not much better. Not much better. 1, 2, 3, 4, 5. Yeah, sometimes if statements are fine. Like, doesn't actually do much good to remove the if statement. It's about as fast as it was before. I think this is maybe a little bit faster than what I had. It's definitely way faster to program. Way faster to program. A lot easier to explain. Way easier to explain. Very clever solution for sure. Not what I went with, not what I came up with, but not bad. Not bad. All right, I think I'm gonna stop there. Take a break. Take a break. Yeah, I think it's better with the if statement. It's easier to read. Yeah, okay, 60%, 70%, whatever. Not too bad. I don't know what the fastest solutions were. I mean, they must be really clever, really fast. I don't know. But this is definitely really quick to program, for sure. Very quick to program. Yeah, you could subtract these, I guess. I don't know if it's much better if you could just do one subtraction here. Technically, it would be a little bit faster if you subtract here, subtract there, and then make this an equals and subtract 1 here. Right, do a few less operations. Just a handful fewer operations. don't know if that really does much, but no. All right, that's probably enough submitting. It's probably enough. There's one with no means be a medium question. That's funny. This is the same one, almost the same one as it's basically the same one as the other solution we just looked at. Pretty much the same thing. And then easy explanation, max moves is not that hard to think about. Same thing as the last one. It's the same thing. These are all the same solution. Am I the only one who came up with a really am I the only one who actually came up with his own unique solution? Really, everyone has the same one. Mine's not that much different. I mean, it's a very similar thing, but it's pretty different. It's quite different. Yeah, solution's actually kind of unique. Yeah. Anyway. This should be very hard. Just a noob at coding. You're a noob. Hard or its explanation is not good. No, it's not. It's not that the question is kind of challenging. It's more so that it's the solution is pretty concise. If you see it, like once you see it, it's pretty. Oh, so you could do with a binary search too. Okay, you could speed up with a binary search. I was trying to find one that's faster. I think the reason is once you see it, it's not that hard to figure out. It's not that hard to program, not that complicated. I think that's why it's a medium. Pretty much what everyone else has, but for what it's worth, does a binary search to locate the windows. Okay, that's kind of cool. I like that. It's faster. A10 login 01. Well, you have to sort it, right? So it's throwing in the binary search to make it faster is cool. I like that. I don't know if it actually makes it faster, but maybe it does. I don't know. For right in range, left bisect right stones right minus n. What does this do? If right minus left, stones right minus stones left is equal to minus 2. Low. Okay, it's like the same thing again. High, we already did that, yeah. Oh, I see. So instead of using the while loop here, you could use a binary search. Oh, that's clever. Yeah, because it's sorted, right? So you can. Oh, okay. Good idea. Let's do that. Update. That's good. I didn't think of that. Didn't even consider that. Stones right minus n. So we're looking for. Could alternatively say plus VSI, right? We're looking for I such that while let's go back. So while VS minus VS of I plus 1, so J doesn't change. J is a constant, right? It is greater than n. We're searching for I. Another way of saying this is VS plus VS of I minus n. We want the largest I such that vs of I is less than this amount. Alternatively is less than or equal to, or if we plus 1, so vs of I is less than this amount, that means it's less than or equal to subtract 1, right? Yeah. So then we want the largest I, such that vs of I is less than or equal to vs of j minus n, which is binary search, lower bound of vs of j minus n. Pointer, lower bound, search for that among vs begin plus I, vs end. Interesting. I don't know if that's much faster, quite frankly. That's a little awkward. Actually, I don't know if that's better. I think it's okay, but it's actually probably slower. Probably not much faster now that I think about it. And then update I to pointer minus vs begin. Yeah, I don't know about that one. That seems kind of weird. It works, I think, but let's try some more test cases. Yeah, am I the only one who didn't do what everyone else did? Am I the only one who actually came up with a unique solution, his own solution, his own thought? It's kind of what I was saying. It was like my main complaint about these. Oh, hello. Ooh. Yikes. Yikes. Ouch. So maybe, oof. Not correct. Okay. Is this still correct? Uh-oh. Let's just make sure this is correct. Okay, yeah, it's still fine. But you can binary search for, yeah, well, huh. Oh. Oh, okay. Yeah, that's my mistake. Okay, I see, that's kind of subtle. It's kind of easy mistake to make. So while it's equal, you got to keep going. So you got to go above VSJ minus n. All right, I think this is correct. Let me try it. Could be wrong. Maybe I shouldn't have submitted. Oh, still got it. Sweet. Yeah, it's not much faster. It's actually not faster. It's actually slower. This is slower to use the logarithmic because you don't need it. You could. It's linear if you do it this way. It's already like asymptotically optimal. It doesn't make it faster. Yeah. No. Don't do that. Mistake. A mistake. Excuse me. Yeah, I think it was actually better the first time I had it, when I did vs of j minus vs of I plus 1 is less than n. It's greater than n. Yeah. And these ones probably should just put these back to where they were, so it's clear what's happening. I like that better. It's really not much of a difference in speed, then probably it's better to have it a little more readable. Okay, I've spent kind of too much time on this. I think I spent a lot of time. Alrighty. Okay. Well, apparently there's a way to do this. That's simple and clean sliding window. This is a good question. This is a good question. I need to stop here though. I definitely need to take a break. That's cool. That's cool. So yeah, I like the solutions that so this was my original solution, which was reasonably fast. It's also linear time and didn't actually need extra memory, but I used extra memory anyway. And then that was the one that I came up with. It took me quite a while. And also sliding window, similar to the other solution, but not quite the same. And then the quite a bit more logic and things involved. The other solution, though, yeah, seems to be actually maybe a little bit faster than their solutions, quite frankly. I don't know. They all seem to be about the same. I think mine was maybe a little bit faster. So that's cool. And then the other solution was use a slightly different kind of sliding window, but the other solution I think is a lot simpler to understand. This is like pretty sophisticated, pretty involved. It's pretty involved. I don't really like it that much, quite frankly. It's like way too much to program. Way too much to program. Way too much to think about too. It's like involves a lot of thinking. So I was right. Yeah, it's like a greedy algorithm is what was required here. A sliding window. I mean, when in doubt, it's probably like a sliding window, or like when it's like really not clear what the solution is, it's probably going to be some DP greedy solution, 2-pointer solution, something that's like it's not obvious. It's probably not very intuitive, but I guess once you figure it out, it's not the worst. Those sorts of questions are not really the ones I'm like very familiar with, I guess. I don't really think about these sorts of things too much. Yeah, like I'm kind of more, I tend to prefer solutions that have like a search space, and you're kind of like searching a search space of solutions where, I don't know, like, I don't even know what to say. Like, I don't know. I don't know what to say here. Like, it's just, this definitely stretches my mind quite a bit. Like, this is definitely not something I would typically kind of think of. Yeah, again, this solution is way more involved than the other one. The other one's a lot simpler to program, a lot simpler to understand as well. And there are a few assumptions there too that are involved that I didn't really think about. One of those assumptions is that you could always move all of the stones into the spots that they need to be moved into, which is like kind of makes sense, but it's also not so obvious. And that not only can you do that, but that'll also give you the minimum element, the minimum possibility. And they just have to handle the edge case when all the stones are already consecutive except for the last one. Yeah. Hmm. Huh. Yeah, it could be the last one on the right side or the last one on the left side that's handled properly. That's the only edge case. I don't know what to say, man. I don't know what to say. Programming is hard. Programming is hard. Yeah. Yeah, I don't know. I don't know. I didn't see it. I didn't see that at all. You could do that. Kind of just miss those things. Hmm. Yeah, I spent a lot of time thinking about this. I don't know, I'm trying to think, like, how could I have seen that? I don't know. That you could almost always move all the stones into a particular interval range. That's a clever idea. And then you can use sliding window over that interval range. And yeah, like I said, like the interval range doesn't have to be all the way, totally encompassing, and you can move things to the right of that range as needed, or to the left. You can extend the size of the range. It's no issue. Basically, always move things around as you need to. It's the only scenario where you run into trouble is, as mentioned, when you have everything consecutive except for the endpoint, where you got to do a little bit like a crisscross type of thing. That's so much simpler than what I did. The logic that I had was so much more complicated. I mean, I was able to, reason it out and narrow it down, but still way more complicated. Excuse me. All right, I think that's probably enough of me looking at this, thinking about this. Let me stop here. So yeah, thank you for watching. I appreciate it. If you like the video, don't forget to like it. If you like the stream, don't forget to subscribe. And I'm definitely gonna take a break now. I don't know what I'm gonna do. I kind of like, I don't know, maybe I'll just lay down for a while. Just kind of think about what just transpired here. I don't know. I don't know. Sometimes they're that simple. Sometimes they're that easy. I think that's why it's a medium, is because you can solve it in a very straightforward way if you see it. But it's maybe if you don't see that, it's like definitely really hard. The way that I came up with was not straightforward at all, but was relatively not too bad. It's pretty involved. That would be kind of like a hard type solution. I kind of the last question we did too was similar, where it took me like hours upon hours, because the solution I came up with was actually like a hard level solution, a variant of the hard solution to a hard question. So it was like hard level. Whereas you could actually have come up with a faster solution that was DP solution that was much simpler to implement. Top-down memoization and a bottom-up DP, both of which were not too bad to program and not too hard to think through. But yeah, you have to see it. I don't know, man. Like a lot of these questions, you kind of have to see the solution, otherwise it's gonna be too hard. I don't know what to say about these sorts of things. Like they're definitely just outside my comfort zone. I think that's kind of why it takes me so long. I'm not like used to thinking about things in that way, in those ways. Yeah. How I typically approach problems is a little bit different than what those sorts of questions call for. I guess. I don't know. I'm not sure. I don't know. I don't know. All right, I'm gonna go. Yeah, thank you again for watching. I'll talk to you soon. Have a good rest of your day, and yeah, I'm gonna stop here. Stop here. All right, take care. Take care. Bye.